with nanostructure. The first manipulation you can see here is spectral reshaping. And actually, I will go a little bit more in detail with nanostructures and spectral reshaping afterwards. So let's see if we can. This is the wrong one.
1 second.
Yep. I think I will start to speak on some color, and then when we get a full color, we will speak later. Just give me a picture, like, doesn't matter which color.
Now color glow.
Okay, so now we have quenching. Okay, is it this like this? Okay, we start with red. Good. No. So. Yeah.
Maybe it would be better to use presenter.
Okay, yeah. Good. So then we have to. Okay, so the first idea to manipulate light is, of course, to switch it on. And once you switch it on, when you think about a nano emitter, it's in terms of excitation. Unfortunately, this nano emitter emits light with not the desired intensity. So the next step of manipulation will be slowly increase the intensity to the desired intensity what we want. So it's the enhancement. Afterwards, like in usual life, when we switch on light, we want to switch just one bulb. So also in nanoscience, we just want to switch 1 nanometer. So selective excitation is also desirable. And the last part of my talk, and also what we in usual life want, is spectral and directional modification. So we have this example, but also the beamer is a really good example. Nanoparticles are a great tool to manipulate light in different ways, like enhance them, redirect fluorescence, and so on. So today I will talk about 2 specific nanoparticle shapes. One are nanostars, the second are P-pyramids. Why metallic nanoparticles are so interesting is due to the plasmonic properties, which is nothing else than the oscillation of the electron excited by light with a certain frequency. They provide a huge scattering cross-section, and they change the local optical density of states, especially in the surrounding of the nanoparticle. They provide high field enhancements. The good thing about nanoparticles is also that by tuning the shape, size, and material of the nanoparticles, we can change the spectral position of the plasmon resonance, as you can see here. Plasmon modes, one can treat them like coupled dipoles in the first order. So when 2 nanoparticles are close together, the plasmon modes can couple. Now the optical properties depend on the polarization, excitation polarization, and one gets 2 different plasmon modes, like the transversal one and the longitudinal one. For the most applications, the longitudinal plasmon mode is more important, since we have an increased scattering cross-section. The resonance redshifts and all the optical properties of the longitudinal plasmon mode are distance dependent. It's so-called the plasmon ruler. And in the near field, the field is localized in the gap between the nanoparticles and highly enhanced. That's why, for historical reason, one call it hotspot. Why such hotspots are interesting? Yeah, first of all, they focus light in this nanoscale volume. So what we get when we place a molecule inside this resonator, we have a high light intensity to excite the molecule. And in these terms, we can enhance fluorescence, or even reshape it, or enhance Raman scattering. The nanoparticles themselves act as a nanoresonator. So once the molecule emits, this emission can couple resonantly to the modes, so the spectrum is reshaped and sometimes enhanced or quenched. Another art of hotspots are provided by sharp features like the single nanoparticles nanostars, so they have lots of tips, asymmetric structure. When they have an asymmetric structure, they exhibit lots of plasmonic resonances in the visible, especially in the region in between, in between 600 and 800. The spectral position depends on the length of the tips, and any polarization can excite another resonance. And from the theory, they are expected to have huge field enhancement located at the tips. It's so-called lightning rod effect. What we wanted is to take these nanostars and due to the asymmetric structure, just excite one hotspot at a specific tip. So in principle, by choosing the polarization and the wavelengths, we wanted to excite, for example, this hotspot or this one, and so on. But when we started to have this idea, there was a difficulty. There were no experimental evidence that the hotspots are indeed located at the tips of the nanostar. And so our idea was first to measure the hotspots in terms of real space evidence and also the strength, and correlated it with the nanostar shape in the hope that we can see where the nanostar has its hotspots. We started a nice collaboration with Fabrice Charrat and Ludovic Doulard in Saint-Clair. And they have this nice setup, which is called photoemission electron microscopy. And this setup allows us to excite optically our nanostars under grazing incidence. We use a pulse laser with a wavelength around 720 till 900 between it in order to match the plasmon resonance. Since we are exciting with optical frequencies, we can change exactly the polarization of our excitation. Afterwards, after a multi-photon process, exactly 3-photon absorption, in the region where the field enhancement is high enough, photoelectrons are emitted, and these photoelectrons we can map with a photoelectron optics, and what we get is a spatial resolution of 20 nanometers, and the white spots are the location of high field enhancement. So in principle, we have now a possibility to map the plasmon resonances with 20 nanometer resolution, and also get the strength of the hotspots by the approximation of the local field. So our electron yield is proportional to the local electric field at the power of 6, since we have a 3-photon process. We did this, and what we can see here is for a certain wavelength, by just changing the polarization excitation, we can excite one hotspot at one tip, either 3 hotspots or none of them. When we change the excitation wavelengths, we can excite different tips. So in principle, this knowledge about the exact polarization and exact wavelengths of the plasmon resonance of the single tips allow us to excite selectively one hotspot at each other located at different tips. Now, we have a nice big hotspots located at the tips, so we want now to enhance the Raman scattering, like in this case. So what we know is that mercaptobenzoic acids can be attached to our nanostars. There were previous experiments from other groups and as well as for our group that in ensemble nanostar enhance Raman scattering. And what you get is this typical molecular fingerprints, the Raman scattering spectra of mercaptobenzoic acid on an ensemble of nanostars. And these two prominent peaks are typical for the breathing modes of the benzol molecule. So, in order to understand exactly where the Raman signals are coming from, we made optical measurements, and afterwards we did a TM tomography of the nanoparticle in order to get the exact shape of the nanoparticle. This exact shape we put in a discrete dipole approximation calculation, and we calculated, taking into account the substrate and the molecule layer, we calculated the region of the highest field enhancement contributing to the Raman. So here you see our reconstructed nanostar. It's a 3D reconstruction. Our nanoparticle looks in this way. We excite the nanoparticle with linear polarization. So we wanted to excite this tip. Unfortunately, when you make the experiment, you are a little bit blind, so we didn't hit it properly. And we measured a Raman signal enhancement. The Raman signal from this single nanostar has an enhancement of 10 to the 7, which is similar to plasmonic coupled nanoresonators antenna. Now when we perform the calculations, what we see, indeed we excite this tip, and this tip has a field enhancement at about 100 times more than the incident field. So the mainly signal of the Raman will come from this tip. But when we compare it to the literature, we know that field enhancement above 10 are sufficient to enhance Raman scattering. So we wanted to be fair and mapped also the region of the field enhancement which are above 10. So in principle, we have two contributions to this Raman signal. One is mainly for this tip, and the rest is from the green marked regions. To prove this one, we change now the excitation polarization by 90 degrees. So now we don't excite this tip. And also our Raman scattering signal in the experiments goes down. And of course we did again the calculations. And what we see, first we don't have any hotspots above 100 around the nanoparticle, but we still have lots of regions with field enhancement which are higher than 10. Now, I showed you how to enhance Raman and how to excite or turn on the hotspots. The next idea is can we turn them off without changing the optical properties? So in the meaning, like this mechanical switch, when I switch it off, I still have the bulb, so when I switch it on, nothing changes. The main idea is to design IFM nanoparticle resonator which you can move with an IFM tip. So Alpan Beck already showed that when you push nanoparticles with an IFM together, the plasma resonance redshifts and also the hotspot inside the nanoparticle increases. That's okay, but it's not what we wanted. And the second one, when the molecule is situated on the substrate, as you can see here, the hotspot is in the middle of the particle. So our first three questions will be like, can we locate the hotspot above the substrate, 1 nanometer? Then can we change the field enhancement without changing the plasma resonance? And the third one, can we move the position of the hotspot or switch it on and off without changing this coupled plasma resonance? And definitely with nanospheres doesn't work. So as you can see here from the publication, this nanoresonator can enhance nicely fluorescence and reshape it, but as soon as you have a molecule located here, it doesn't work. So what we wanted to do is to change the nanoparticles. And when we go to B pyramids, like you see here, first of all, what one can see is that the B pyramid is located in such a way on the substrate that one tip is always on the substrate, as you can see here in the cross section. And it has a longitudinal plasma resonance which is quite sharp. So the red dot are scattering spectra measured, the black dots are simulation with FTTT. And as you can see here in the near field distribution around such a B pyramid on a substrate, the field enhancement can be located on the substrate. The second thing what B pyramids make them unique is when we make nanoresonators, pairs of nanoparticles, we have a unique possibility to make 3 configurations, like both tips down, both tips up, 50 nanometers in the air, or 1 tip down, 1 tip up. So this is actually the idea, and we started to push the nanoparticle around to form the nanoresonator. So you start with randomly distributed, and we make our nanoresonator. And actually to move B pyramids with an IFM cantilever is not so easy like a sphere. While in a sphere, you just push them straight away, like in soccer. In the B pyramid, you have always to tilt it and go around till you reach the final position. So what we did is Here's something like a real-time movie of the movement of the B pyramids, so it takes a while till you bring them together, and then you have to manipulate them on a finer scale. So on the lower graph, one see the movements of each nanoparticle. So the red arrows indicates each tip position and each pushing mechanism. We form these three configurations, like both tips down, one tip up, one tip down. So these are quasi 3D images from the FM, and these are the corresponding cross sections. And now the main question is, can we mechanically change the configuration without destroying the nanoresonator? So what we want is to just push this tip of the B pyramid and change the configuration from both tips down to this configuration where one tip is up and one tip is down. So we did this. We applied force on this tip, and afterwards we switch the configuration. Good, this till now was something like nice tricks to move particle around, but why did we did this? Let's take a look to the optical properties. So in the nanoresonators, we have all the time the similar optical properties. So in these both configurations, the coupled plasmon frequency has the same value. When we change the configuration, we had a slight blue shift, but in principle, we still have the same optical properties. When we go now a little bit a step further and we look at the field enhancement, we see first we can locate the hotspot on the substrate, raise it above, and even to 50 nanometers. So what we can do is, first of all, place a hotspot on the substrate. Second, we can increase the field enhancement on a specific position in the gap in between the nanoparticles without changing the optical properties. And the third, of course, we can move it up and down. So we have a nanoresonator where slowly we can increase the intensity of the hotspot. Good, that was everything about, I have to check the time. Okay. We went now to larger area arrays in order to spectrally and directionally reshape the emission. Also, small particles can reshape the fluorescence emission, but when you think about a device, you need a little bit of large-scale arrays. So in the literature, there are lots of arrays which can reshape the fluorescence, either emission, either directionally or spectrally. So you start with nanoparticle arrays, dimer nanoantenna arrays, or even more complicated structure like this inverted opal, which provides localized surface plasmons and a propagating surface plasmon. And the most famous one is the bullseye aperture for fluorescence sorting. The drawback of these devices is either they are non-transparent, so you are restricted in the measurements, or they are prepared by e-beam lithography. E-beam lithography is time-consuming, expensive, and the working area is limited. So when you want to make something like a large area array, it will take lots of time and it doesn't pay off. What we did is use a self-assembly technique. My colleague Boyang Ding from JKU was or is the expert in preparing self-assembly opals of more than 5 layers together. So we apply this technique, and how we do it? We take polystyrene spheres, let them on a substrate self-assemble. After a while, we get a nice hexagonally packed monolayer of the polystyrene spheres. We evaporate silver on top of it, and what we get is our dielectric structure, a photonic plasmonic crystal. So we have polystyrene spheres, 390 nanometer, silver capped with 40 nanometer silver, and here you can see the SEM image. And since we want to manipulate light, instead of using plane spheres, we use dye-doped spheres, and with the emission and absorption spectra. So the absorption was 470 roughly, and the emission, the main emission, roughly 510. And our sample, in contrast to other one, is transparent. So we can perform reflection transmission measurement, angularly resolved, as well as angularly resolved fluorescence measurements. So in order to understand exactly how our photonic plasmonic crystal will reshape the fluorescence, we have three kind of reference samples. So the first one is an unstructured dye-doped polymer film. The second one is a photonic crystal, the monolayer of polystyrene spheres. And the third one is our hybrid structure, the silver-capped polystyrene spheres. So when you take a closer look to the normal emissions detected in the normal direction, what we see is the plane film has the same emission like the polystyrene spheres in solution. When we change it to the photonic crystal, we see a spectral reshaping. But still, when we detect from the air side or to the glass side, this fluorescence is not, doesn't change. So it doesn't matter in which direction we detect it. This is different when we look at the fluorescence from our photonic crystal. So the fluorescence to the air side is reshaped, and the fluorescence to the glass side is reshaped in a different way. So from the normal emission spectra under normal detection, we cannot get any information in which way or which coupling mechanism exists. That's why we had to define a spectral reshaping factor, which is nothing else than for a specific wavelength and angle, the intensity of our structure normalized by the intensity of the smooth film. And when we now look at the dispersion relation of our reshaping factor, we see that for S and P polarization, we have some dispersive features in this reshaping factor for the fluorescence to the air side. The same holds also for the fluorescence detected from the glass side. We have two dispersive features. In order to understand in which way this fluorescence is reshaped, we compare these reshaping factors with transmission for the air side, since the optical path is the same to the structure, and with reflectance from the glass side, which is corresponding to the optical path for the fluorescence through the glass side. And what we can see is, following this dispersion relation, we have the same dispersion in the optical spectra, like transmission or reflection. And this dispersion, the black lines are the photonic crystal modes, theoretical calculated, and the color plot represents the measured data. So we see that our fluorescence couples to the photonic crystal mode and shows the same dispersion. Now when you take a closer look to S and P polarization, you see that there is a slightly different behavior for S and P polarization. This comes because we have a hexagonal lattice, and S and P polarization coupled to different photonic crystal modes. When we make the same analysis for our photonic crystal hybrid structure, it's a little bit complicated to see something out of these graphs. So what you see, lots of features, but they are in a small featured area. So that's why we switch back to the usual 2D graphs. And when you see the fluorescence to the air side, you see at around 500 two dispersive features. These dispersive features are similar to the case of the photonic crystal, so it's purely coupling to the photonic crystal modes. But when we go now to the fluorescence of the air side, we see the dispersive feature coupling to the photonic crystal mode and a non-dispersive feature at around 580 for S and P polarization. And this non-dispersive feature we can attribute to localized plasmon modes, exactly void plasmon modes. So our structure exhibit at around 580 a void plasmon in the cap, in the silver cap. While at 500 there is not such a dipolar void plasmon resonance. When we now want to quantify the directionality of our fluorescence modification, we have to determine the number of the photons emitted in a specific solid angle and normalize it by the total number of the photons, and we do it by this formula. And we analyzed our directionality for the spectral region of the dispersive feature and for the spectral region of the non-dispersive region. When we start with the plane film, what we see is nothing special. So in the upper part is air, fluorescent to the air. In the lower part, fluorescence to the glass. We have S and P polarization. And what we see is the green light dots are experimental values, and it's a purely cosine square behavior. And of course, the same for 580, the region of the non-dispersing feature in our former fluorescence spectra. When we take now a closer look to the photonic crystal modes, what we see is that for small angles, we have a deviation from this cosine square behavior. Unfortunately, you cannot see it, but there are, again, the blue dots are experimental data, the black stars are theoretical data, calculated one. And when we change now the spectral region, we see again two different lobes for higher angles. This is a purely coupling to the photonic crystal modes of the emission. So smaller wavelengths, smaller angle, higher wavelengths, higher angle, and here one sees again the different coupling for S and P polarization in both cases. What we also see that doesn't matter if we look from the air side or to the glass side, the spectra has the same directionality in both cases. So we wanted to understand a little bit more, so we performed calculations. FDTT, we had a huge monolayer of nanospheres. In the central nanosphere, we placed a dimolecule, which was simulated like a dipole. And we look at the field distribution inside this monolayer. So for 500 nanometers, we see here a coupling in the monolayer. So it's a coupling to the photonic crystal modes. And when we switch the wavelengths, we see a different art of the coupling. When we make the same analysis for our photonic crystal system, first of all, we see for the spectral region at around 500, where the dispersed future was, a similar behavior like in the photonic crystal mode, but still it's a little bit more deviation that from the photonic crystal for the cosine square mode. And also the upper and lower part of fluorescence is different. One comes because of the silver caps, and the second deviation is we still have the strong coupling to the photonic crystal modes, but now our void plasmon exhibit also some multiple modes in the void, and the P polarization can couple to it. So in the terms of the region of 580, what we have is a change in the overall behavior. So first of all, the fluorescence to the air side is reduced, and we have a forward beaming effect. This is a pure evidence to the coupling to the photonic crystal modes, to the localized void plasmon modes. The void plasmon, it's a spherical cap, so it's symmetrical, and S and P polarization couple in the same way, and one can imagine it acts like a mirror, so it beams all the luminescence forward. Of course, we did the same simulations, and what we see is here a coupling to the photonic crystal mode, and also the coupling, the weak coupling to the multipolar void plasmons. And when we compare to 580, we see exactly in this near field distribution a clear forward beaming. What's also interesting, we have also propagating surface plasmon modes. The coupling to the surface plasmon modes in our case is negligible. Doesn't matter which wavelengths we looked at. Both in experiments and theory, we saw that. Actually, in this picture, one can see a weak coupling to the SPP. With this, I want to thank to all the nice people who contributed to this work, especially Thomas Klar, Bojan Nikita, Arnold, and Goran Isic from the Institute of Applied Physics. Also, the team of Professor Feldman in Munich, where I did my PhD, like Joachim Ster, Moritz Ringler, Lidau Sinka, Frank Kekel, and C.G. Wu, who started with me the manipulation of the B pyramids. The team of Fabrice Charrat with Ludovic Tourin and Guillaume Lorrain for the nice beam measurements, and for the nanostars like 3D modeling, TM tomography, and lots of experiments, the team of Eduardo Conrado and his student Eduardo Perassi, and also the team from the LMU with a high resolution microscope, Markus Döblinger and Alexander Wisnet. Thank you very much for your attention.
Questions?
One question about your notation, fluorescent reshaping. Please explain me what does it mean, the first and the second. the picture. How do you get this picture? The second from the the last your slide, the last your yes last. Oh, this also on
This one?
Yes, this one.
Okay.
Okay,
Yeah.
and what does it mean? The first fluorescent reshaping.
Okay, fluorescence reshaping. It's how we define it. So in principle, we had this spectral reshaping.
Only the fluorescence shape of the band. Yes.
This one is for normal incidence, and we performed angular resolved measurements. So, and we had to quantify both what happens for a specific wavelength and under a specific angle. So we detected the emission for all the angles. We had the full spectra, and then we use this reshaping factor to quantify it. So what you see here is here's a measurement of the degrees, and here is a spectra. So when you cut it in this direction, for each angle you have a spectra. And the reshaping factor, it helps us to understand the pure contribution of the structure. So we neglect any cases of. And the second, the second thing, it's this picture is nothing else than the result of simulation, FTTT calculation.
It is calculation.
Yeah, so we calculated it, and it's a cross cut through the multi-layer.
I am Vitaly Betsuk from Kyiv. Did you take into account the longitudinal electromagnetic modes in nanoparticles? I mean modes in which electric field is directed in the same direction as the wave vector. These modes are sometimes called acoustic electromagnetic modes.
Okay. As far as I know, but I might be wrong, for the nanostars and the small nanoparticles, they have some reading modes, but they are quite fast, and I never observed them in experiments.
They could shift plasmon resonance, maybe blue shift. There can be additional shift of the resonance.
We observed this type of difference when we compare our beam spectra with normal scattering spectra, but this is due to the oscillator strength and near and near field shifts.
And another question, how large is the melting temperature of golden nanostar? Do you know?
Yeah, it depends. So let's start since you have a nanostar with tips. So the melting temperature of the tips is something like 305, and the melting temperature of the gold, I would say it's roughly 800. I have some simulation and some measurements, and so maybe in the coffee break I can show you exactly how you can reshape also with optically the nanostar.
Did you observe the same enhancement for all the Raman bands of your gold molecules? For instance, what about for carbon surface stretching?
Yeah, actually, I have to say we really concentrate on these two modes, and sometimes we observe also an enhancement of smaller modes. But actually, we were more interested to use Raman enhancement like an indicator of our hotspots and the optical properties. So we didn't try to identify other modes. So in principle, might be that one will see the same enhancement, but I would not say like this because of the orientation of the molecule and different things. So.
As far as I understood, you excite your like fluorophore in when the plasmon overlapped with absorption, and you obtain enhancement of in emission. Just a question: if you consider
in which experiment? Sorry.
In that experiment when you covered silica particles with,
so in this one
metal, yes, and then also you have some diamond.
Actually, the excitation is non-resonant to any of the structure. It's just resonant to the absorption of the molecule.
Okay.
So, in principle, what we make is we excite with 404, and this is on this side of the absorption spectra. So we don't have, or let's say, really weak contribution to the plasmonic features and so on, even if we have silver. So the resonance of the caps and so on is much more redshifted compared to our excitation wavelengths.
And what will be if we will excite it more with in resonance with emission?
Okay, so when we excite it somewhere here, so
Yes.
we coupled with the emission and so on, we had for smaller spheres we see fluorescence enhancement. Or here, when you take a closer look to this spectrum, we see more like the intensity goes down. For smaller spheres, when we excite it resonantly, we get an enhancement here.
But is it stronger than in the previous case when resonance, plasmonic resonance with absorption, or it's like the same?
It's hard to say because there are different coupling mechanisms. We lose this coupling to the photonic crystal modes a little bit. That's why we get a little bit more enhanced. So, but I would say it's stronger. So the localization of the hotspot it's better in the smaller spheres.
Thank you.
Thanks.
Is how powerful can be this material as a light emitter?
Oh, that's
Can it be used as an illumination device?
Yes, in principle. So we are working to make something like a nano laser out of it, and it will work, but it will not work like I turn it on and it will give me power. So one have to pump it really hard, and that's a point. So the power which we expect, or let's say the illumination behavior, one can use it like an emitting device, but the energy which one have to bring inside is also so big that it will not work out like putting in to illuminate something. It's more for small application, like when I want to have a local illumination source.
Thanks.
Thanks for interesting